JavaScript is at the heart of modern web applications, empowering developers to build dynamic, interactive experiences. But with great power comes great responsibility. JavaScript closures, while immensely useful, can become a double-edged sword if not used correctly. Imagine building a sleek web app, only to find it sluggish and unresponsive due to hidden performance pitfalls. Understanding closures isn't just about writing functional code, it's about crafting efficient, maintainable applications that scale smoothly with your needs. In this tutorial, you'll learn how to leverage closures effectively, avoiding common traps that can lead to memory leaks and performance bottlenecks. By the end of this session, you'll have the tools to write cleaner, more efficient JavaScript, ensuring your applications run at peak performance. Dive in with us to explore how a deeper understanding of closures can elevate your coding skills and lead to faster, more reliable applications. And if you find value in this tutorial, subscribe to our channel for more insights and strategies that keep you ahead in the fast-evolving world of web development. By staying updated with our content, you'll continuously sharpen your skills and stay at the forefront of the industry. Let's delve into the concept of closures in JavaScript through the lens of lexical scoping, a fundamental aspect that underpins how closures function. Imagine your code as a series of nested boxes, each representing a scope. These boxes are organized in a hierarchy, from the global scope down to the innermost function scope, creating a stack-like structure known as the scope chain. Closures enable a function to remember the state of these boxes even after they have been closed and put away. This characteristic is what makes closures so powerful. They maintain access to variables in their lexical environment long after the outer function has completed execution. For example, consider a function outer that defines a variable x and returns another function inner which uses x. This returned function inner retains a reference to x even after outer has finished executing. This memory retention is possible because inner forms a closure over x, preserving its state. Such encapsulation allows for private state retention and data hiding, much like a safe deposit box that only you can access even if it's stored in a bank vault that closes at the end of the day. However, it's crucial to manage what these closures capture. Otherwise, you might inadvertently keep old, unnecessary boxes open, leading to memory leaks. Understanding this foundational theory allows you to grasp why closures can be both a boon and a bane in JavaScript development. Now, let's explore closures from the perspective of garbage collection and memory management. Think of your JavaScript application as a bustling city where each function and variable is a resident. Closures, in this analogy, are like residents who keep mementos, snapshots of certain aspects of the city that they hold on to even if the original locations are modified or demolished. While these snapshots are often necessary for the residents to carry out their tasks, they can also lead to overcrowding if not managed properly. JavaScript's garbage collector is responsible for cleaning up and reclaiming memory from variables that are no longer in use. However, closures can complicate this process by holding onto variables within their captured scope, preventing the garbage collector from freeing up memory. This is akin to a resident keeping a room full of old newspapers that should have been recycled. To avoid such clutter, developers must be vigilant about what data closures retain and ensure that unnecessary references are eliminated. For instance, if a closure holds a reference to a large DOM element that is no longer needed, it can lead to a memory leak, much like a resident occupying valuable space with obsolete items. By understanding how closures interact with the garbage collector, developers can better manage memory usage, ensuring that their applications run smoothly and efficiently without unnecessary baggage. In this code example, we demonstrate the use of closures within a React component to manage state effectively and avoid common pitfalls. This example highlights how to use the useCallback hook to memoize functions and prevent unnecessary re-renders, a common issue with closures in React. The counter component utilizes a custom hook, useCounter, which encapsulates the state management logic for counting. By employing closures, we manage the state of the counter without resorting to class components, thus leveraging functional programming paradigms. This supporting code file includes utility functions that can be used across different components in a React application. The utility functions leverage closures to encapsulate logic and maintain state where necessary. In this example, we show a simple utility function that creates a debounced version of a function, helping to optimize performance by reducing the frequency of expensive operations triggered by user actions. Here, we present the configuration file for the React project. The package.json file includes metadata relevant to the project, as well as the list of dependencies required to run the application. This file is crucial for setting up the development environment and ensuring all necessary packages are installed correctly. It enables seamless project initialization and management with Node.js. Start by navigating to the web page designed to demonstrate Clojure performance. As the page fully loads, it presents a welcoming title confirming the focus of the demonstration, Clojure Performance Demo. Initially, the display shows a count, clearly indicating a starting value of 0. The demonstration involves interacting with an increment button prominently placed on the page. Upon clicking this button, the displayed count updates, reflecting the change from 0 to 1. This update is immediate, underscoring the effectiveness of closures in managing state changes efficiently. A second interaction with the increment button further increases the count, this time from 1 to 2. The seamless update highlights the responsive nature of Clojure-based state management. For comprehensive visibility, scrolling down the page ensures that all relevant content remains accessible and visible, allowing viewers to engage with the demonstration fully. This interaction exemplifies how closures can be effectively utilized to maintain and display dynamic state changes in a user interface. As we wrap up our deep dive into JavaScript closures and their impact on front-end performance, it's essential to internalize the key takeaways that can fundamentally transform your approach to web development. By mastering closures, you unlock a powerful toolset for efficient state management and encapsulation. This understanding not only prevents common pitfalls like memory leaks and unnecessary re-renders, but also streamlines your code for better maintainability and scalability. Imagine the time savings and reduced frustration when your applications run smoothly without unexpected performance hiccups. Picture yourself confidently applying these techniques in real-world projects, leading to faster, more responsive applications that delight users and stakeholders alike. Now, what should you do next? Start by implementing these practices in your current projects. Test the impact and refine your skills through hands-on experience. Keep an eye on emerging JavaScript patterns and incorporate them to stay ahead of the curve. By subscribing to our channel, you gain access to a wealth of resources designed to accelerate your learning journey. We focus on delivering clear, practical examples that are immediately applicable, ensuring you don't just learn, but truly understand and apply new concepts to enhance your professional toolkit. Stay with us, and let's continue to elevate your coding prowess to new heights.